Hello, today Antonio and I will be presenting on a topic from Chapter 12, Bernoulli's equation. In this presentation, we will be covering the following. First, we will touch on the background of this equation, then how it relates and is founded in the law of conservation of energy. We will also break down the components of Bernoulli's equation. Antonio will then discuss and give example questions as a deeper application of this concept. And lastly, of course, will be the listed references used throughout this presentation. So let's begin with a little bit of an introduction to Bernoulli's equation. Daniel Bernoulli was a Swiss mathematician who developed Bernoulli's principle and equation in his 1738 book titled Hydrodynamics. This principle is a fundamental process in fluid dynamics and follows the law of conservation of energy, which, if you recall, states that energy cannot be created nor destroyed, but rather is conserved and changed. Bernoulli's principle states that as the speed of a moving fluid increases, its pressure decreases. Now, this principle takes into account three main components of moving fluids, which are pressure, fluid density, and velocity, and how they interact with each other to maintain a constant sum. The law of conservation of energy is crucial to understanding Bernoulli's equation. It is relevant as, according to Euron and Hinrichs, it applies to Bernoulli's principle as the net work done by the fluid's pressure results in changes to the kinetic and potential energy of the fluid. Additionally, the sum of the pressure, kinetic energy, and potential energy stays continually constant, as we can see on the equation diagram to the right. For example, when the height of a fluid increases, so think of an elevation point from the bottom to the top of a mountain. Well, that elevation, that increase in height, will cause the potential energy of the fluid to thus increase. Consequently, the pressure and the kinetic energy would decrease as the fluid slows down. This would ensure that the sum remains constant throughout the changes in fluid components. Overall, as a fluid moves and its factors change, the kinetic potential and pressure energy change to maintain a balance and constant sum with each other. Now, we are going to break down and compartmentalize Bernoulli's equation. So let's take a look at the first section of this slide. Bernoulli's equation states that for an incompressible, frictionless fluid, the following equation is true and has a constant sum. The equation reads uppercase P plus 1/2 PV squared plus PGH equals to constant. So let's take a look at these variables and break down their meanings. First, we have an uppercase P, which would represent the absolute pressure of the fluid. Lowercase p would represent the fluid's density, lowercase v, the velocity of the fluid, lowercase h, the height, and lowercase g we know to be the acceleration due to gravity, which is also a constant value. Moving on, as the total remains constant, any 2 points chosen along the fluid's path of movement can be shown as the equation becomes the following. P subscript 1 plus 1/2 PV squared subscript 1 plus PGH subscript 1 equals to P subscript 2 plus 1/2 PV squared subscript 2 plus PGH subscript 2. Since our sum remains constant, as we saw in the first equation, every point in the fluid's path of movement can be equally compared to each other. On the left side, we have our first point, and on the right side, we have our second point along the fluid's path. And that is shown with our subscripts 1 and 2. Lastly, we recall that Bernoulli's equation follows the law of conservation of energy. In the equation, 1/2 PV to the squared power represents the kinetic energy portion of the equation. PGH represents the potential energy portion of the equation, and this can be visualized as follows. We have 1/2 PV squared equals to 1/2 mv squared over uppercase V equals to kinetic energy over uppercase V. Now, if you take a quick look at the second middle part of this top equation on part 3 of this slide, we'll see that 1/2 mv squared is the equation that we learned for kinetic energy. So when we're breaking down this component of Bernoulli's equation, this is simply stating that we have kinetic energy over volume is the same as 1/2 PV squared. And the same principle follows for PGH, which states that mgh over V equals to the potential energy over V. Now, V again equals to volume, and mgh is the equation for potential energy.
Hello, my name is Antonio Luna. We are going to be going over a few examples on Bernoulli's equation just to get you guys to see what kind of problems you might be getting on any assignments, projects, or any upcoming tests you might have on Bernoulli's equation. It can seem quite daunting at the beginning because of the big numbers and especially because of how long Bernoulli's equation looks. But after these examples, you should see it's not hard like at all really. It's just basic algebra. You just really need to know what numbers to put where, and depending on what question you get, you might have to jumble around Bernoulli's equation to get the answer you're looking for. But other than that, it's pretty simple. So we're going to start with the first example here. Water flows through a pipe that rises 3 meters between 2 points. At the lower point, point 1, the pressure is 200,000, the velocity is 3 meters per second, and the elevation is 0. At the higher point, point 2, the velocity is 2 meters per second. What is the pressure at point 2? And of course, under that, you see we have the density of water and gravity. These are going to be your constants. They're not going to change unless you're working with another liquid other than water. And if you're working on another planet, then you might have to, change the gravity and then the density depending on what you're working with. But we're just going to work with water and the gravity on Earth for now. We don't want to get too complicated now. So we're going to start with Bernoulli's equation. The Bernoulli's equation is the pressure at point 1 plus 1/2 times the density of the liquid times the velocity at point 1 squared plus the density of the liquid times gravity times the height at point 1 equals the pressure at point 2 plus 1/2 times the density of the liquid times the velocity at point 2 squared plus the density of the liquid times gravity times the height at point 2. Now, since we're looking for point 2 and the question kind of already gave us all the numbers we need other than point 2, it's pretty easy. We just have to plug in everything and then just solve it down algebraically. So our givens are the pressure at point 1 equals 200,000, the velocity at point 1 is 3 meters per second, and the velocity at point 2 is 2 meters per second. We have the height at point 1 equals 0 meters, and then we have the height at point 2 equals 3 meters. And of course, we have our constants. Now we're just going to basically plug everything in, like I said, which is going to give us this 200,000 plus 1/2 times 1,000 times 3 squared plus 1,000 times 9.8 times 0 equals the pressure at point 2 plus 1/2 times 1,000 times 2 squared plus 1,000 times 9.8 times 3. And now all we're just going to do is, multiply everything on both sides, obviously, which is we're going to get 200,000 plus 4,500 plus 0 on the P1 side. And the P2 side, we're going to get P2 plus 2,000 plus 29,400. And then just do that one more time, add all of those numbers, that we're going to get 204,500 equals P2 plus 31,400. Now we're looking for P2 obviously, so just do some basic algebra. We're going to get P2 by itself. So we're going to subtract 31,400 from that side and put it to the other side, which is going to give us P2 equals 204,500 minus 31,400, and then just subtract and we get P2, which is going to give us 127,100. Now this is a pretty easy question since it kind of gives us all the things we need, other than the thing we don't need. This next question is a little tough because it doesn't really give us the numbers. It kind of just gives us hints at what the numbers are. So here's the example. A tank is open to the atmosphere and filled with water. A pipe is connected near the bottom of the tank and leads 5 meters vertically down to a spout open to air. Assuming negative velocity at the water surface and no energy loss, what is the speed of the water as it exits the spout? And of course, we have our constants like the last example. Now, our givens, this is a little tough, so this doesn't really give us any numbers. Of course, it gives us our constants. It gives us height 1, which is going to be 5 meters, and height 2 is going to be 0 since it's the bottom of the tank. Velocity at the top is going to be 0 meters per second because it says it's a large tank, and when it's a large body of water, the velocity at the top is going to be negligible, so it's going to be around 0. So we're just going to put 0 for the velocity. It also says that um, the top and the bottom are both open, which would mean that the atmospheres would be the same, meaning the pressures would be the same. So the pressure at point 1 and pressure at point 2 would be the same, basically making them cancel out. So we're just going to put that as 0. Now we're going to start with Bernoulli's equation. We're going to mix it around though because we need to look for the velocity at point 2, and we can't really do that with this equation. So since the velocity at point 1 and the height at point 2 are both 0, we can get rid of the 1/2 times PV1 squared, and we can also get rid of the PGH2 because they'll just equal 0, which will leave us with P1 plus PGH1 equals P2 plus 1/2 PV2 squared. And then, of course, we can cancel out the P1 and P2 since, like I said, they are going to cancel out anyway since the pressures are the same, which is going to leave us with PGH1 equals 1/2 times PV2 squared. And then we're going to mix it around. Since we're looking for V2 and it's squared, we are going to get rid of the half and just put 2, and then we're going to square root the whole thing. And that is going to be, this is going to be the equation we are going to be using. So all I have to do now is plug in. So we're going to get the square root of 2 times 9.8 times 5, and it's going to equal 9.9 meters per second. Of course, it's going to be like this. If for other things, we could go over like more, but it looks like we're running out of time right now. Thank you for sticking with me and Jenibelle. I hope you learned something, and good luck on any of your test assignments, and have a good day.